Okay, so my setup might be a bit crude. I suppose I could do this on the computer as well, but I happen to have the drawing sitting out, so we're just doing it this way. So here's the schematic for this power driver card. And as I was mentioning, my goal here was to have something that could digitally switch the power out to the tool for heaters or for controlling tool power, such as a router. Fast, easy, and relative to PWM control. And this is what I came up with. It's based primarily on a Linear Technologies LT1161 quad protected high side MOSFET driver. So it uses MOSFETs, the IRF Z34Ns. And what it does is it takes a power in, which can range anywhere from a few volts, say 5 volts, all the way up to 60 volts. So it can handle the 24 volt or 48 volt that I have in my system, and then takes a PWM signal in and switches it. So here we go. Here's the input for the power. So this is your power in that you're going to be regulating, as well as 5 volts and ground. Down here we have our PWM input, and it comes to an optical isolator and into the LT1161 high side MOSFET driver. Those will go ahead and switch our MOSFETs, which are here. But this chip also has a bonus feature where it does current regulation, so you can design in certain resistors and capacitors, reference capacitors and precision resistors here, and set it so that you have a current limiter as well. In my case, I wanted 3 amps so that I wouldn't put too much current through the cables that go out to the tool head. So that's what those components do. And then there are some flyback diodes here, because this board is going to drive not just resistive loads such as a heater, it drives things, inductive loads like motors. You want a flyback diode because that motor will keep on spinning after you shut off the power, and you need to be able to handle that. So that's what these flyback diodes do. The one thing this board will not regulate well is the capacitive loads. So it works great on resistive and inductive loads, which are really what the tool has. Does not work well with capacitive loads. And so these MOSFETs, these 4, handle the 4 channels of output based on the 4 channels of PWM input. This side of the board does a couple of things. Right here, it has 4 more MOSFETs that actually take the feedback from the original 4 and give a status output. So if you're looking to close the loop to make sure when you turn one of these on, you're seeing an output other than at the device, you can actually monitor it on this side. So it gives you just a plus or minus 5 volt to let you know that it's on or it's off. And then the lower part of the board is a input with voltage. So this is basically used to drive thermistors and RTDs. So it takes 5 volts, runs it through a resistor, a 560 ohm resistor, out to the device, then receives the input from the sensor back in, and allows you to tap that through these 4 pins and run that to an A to D and see what the resulting voltage is. In physical reality, this is what the board looks like. Again, here's the, let's see if I can get an angle that you can really see it. Here's the power input. Here's our PWM input right here. Opto-isolator, capacitors that regulate the current limits, the high side MOSFET driver, the actual MOSFETs that do the work, the MOSFETs that do the, I'm sorry, these are the MOSFETs that do the work. These are the MOSFETs that do the sensing, whether it's on or off, flyback diodes, power output, and the input for things like RTDs and thermistors. And then their signal comes out here.